this computer. Okay, cool. So to minimize background noises and make it easier to hear our speaker, I'll request all of you to mute your microphones unless and until it does not require. Thank you, guys. Let's wait a few minutes so that everyone could join before we start today's main session. In the meantime, I will give the short description about our team and its goal. Our team, called Tech Enthusiast and Software Engineering Group, organize the tech and software related webinar session on every 2 months. Anyone who are interested in software and technology could join the session. Our goal is to share the tech and software knowledge among each other, so we not only welcome anyone, but also encourage everyone to give the presentation on their expertise topic. Of course, giving presentation is not the mandatory. We had the first webinar session 2 months back, and we introduced our group, its goal, and other group related stuff in that session. This is the second webinar session that has been organized in this group. I saw like some new faces, and I really want to introduce with each other, but we have limited time. But no worries. Actually, I have created the Slack and LinkedIn group. I will inbox those links to you guys. Hope you guys will accept and be the member of those groups. Okay, it's 9:02. Let's start our today's main session. Prakash will take it from here. Thank you. Let me make you the host, Prakash. Change host. Okay, now you are the host.
Yeah, thank you, Sonic. Yeah, so I'm going to try to do it through video today, where I have recorded a video series just for this presentation, and I'm just going to play it through YouTube, and it's going to be available after also, so so that it's a reference. And the video has segments. I'm going to go through about 6 segments today, and then I'm going to pause in between if there are questions or just for discussion in between. So please feel free to interrupt me in the video, through the chat or just through speaking out, and then I'll pause the video and go from there. Let me see if this technology will work. So I'm sharing a Google Chrome window, and this is the first portion, and I want to make sure that I'm sharing sound. And hello, technology enthusiasts. So just to confirm, when I played, did people hear the sound? Yes, group. Today, I will talk about creating a sensor and actuator net. Are you able to hear the sound?
Yes, I am able to hear the sound.
Okay, then I'll go full screen and play the video, and then look for comments then. Network that can be remotely controlled and monitored from across the world. We will break down the workshop into 8 short segments of about 5 minutes each. First of all, I would like to thank Sonic Mulla for organizing and providing me the opportunity to give this TED talk. The audience of this talk is, as the name indicates, technology enthusiasts who want to learn about designing and developing systems using the Raspberry Pi for personal use. I firmly believe programming and system design is just a tool. People from different backgrounds and skill levels can self-learn to develop systems from free and open source software components and hardware that is readily available. Definitely,
Students who study computer science or do this professionally may still find the content helpful as a refresher. This talk is generally intended for an audience who don't have a background in computer science and programming. I have been fortunate to be surrounded by students and colleagues who are just beginning their high school studies. Some of you are finishing up your physics or mechanical engineering undergraduate or graduate degrees. You remind me of my high school days when I first fell in love with tinkering with software and electronics. The agenda for today is the system that we are going to design and code. What do you need and how much does it cost? The block diagram, the user interface, server architecture and code layout, client architecture and code layout, integrating it all together, testing the subsystems at the interfaces, and summary. On what we are going to design, purely for learning purposes, we are going to design a sensorized garden system. It will have pumps to pump water from reservoirs and sensors to measure moisture, temperature, light levels, and humidity. This is a fun project for me because my mother is a botanist and I grew up spending a lot of time in our home indoor and outdoor gardens. One of the first projects I did as a high school kid was to control a pump. It was a purely electrical control system for detecting the water level in a well. I followed a tutorial like this in a hobby electronics magazine popular in South Asia called Electronics for You. I encourage the audience to get their hands and minds occupied and try this, not just for this particular problem definition, but also for other similar problems. In fact, this project follows a system I architected for a Massachusetts Institute of Technology student entry to a NASA competition to drill for ice on Mars. I would like to thank the kind support from various organizations we have received for that project. We use the same system to control robot positions, drills, heaters, water pumps, and read sensor data such as vibration, power consumption, and drilling force. In a test we are planning in a few months, thanks to our friends from the Asclepius project, analog astronauts will control the robotic system from across the Atlantic using the internet. Now, back to the system we are describing in this talk. I named the system Aveti. For those who are not familiar with engineering projects, the system designers often name their projects and products to refer to them conveniently. The code for the project is open source and is available in the linked GitHub address. What does Aveti do? The two main functional areas of Aveti are to continuously monitor plants and provide them with the water they need automatically. Another function is for the data on temperature, humidity, light, and soil conditions to be available for remote monitoring and to be able to perform manual interventions remotely if needed. If you are interested to learn more, join us for part 2 of this talk. Hello, welcome to the second part of this series on a sensorized garden.
So before I move to part 2, I'd like to break it here so that it's not monotonous and see if anybody has any questions.
Just curious, like I have not get a chance to work in the Raspberry Pi or like has been implemented through the protocol gRPC. Other than Prakash, does anyone has experience?
No, it's new to me as well.
Yeah. Okay, let's continue, Prakash. I hope like might be once we go to part 2, 3, we might have more questions.
Sure. So
in this part, we will talk about the bill of materials used to build the system. We will then briefly discuss the hardware design choices before moving on to the software design choices. We will not talk too much about the hardware design, as we are mostly buying parts off the shelf and not designing them ourselves. Each of the sensor and actuator components could be an interesting topic on its own. On the hardware bill of materials, I realize I have an international audience here. Currently, I live in the United States, and it is relatively easy and cost-effective to source these components. When I was an engineer in Nepal, it wasn't easy to source these components. If anyone in the audience wants to build this or similar systems and has difficulty sourcing the parts, I would be happy to discuss and assist. Also, please feel free to comment on the video or the GitHub site on availability and alternatives. First, the Raspberry Pi. For this project, it is likely that a lower cost version like a Pi Zero will also work. However, if you are not budget constrained, I would encourage you to get the Pi Model 4B here, as it is much easier to set up and run the Python software and library modules. It's easier to load the Ubuntu operating system with a higher end computer. If you manage to get it working with a lower end Raspberry Pi, leave some comments and we'll also document it in the GitHub repository. The resistive soil moisture sensor here, the resistive soil moisture sensor measures the moisture near the plant roots. As the name implies, I specified one that is corrosion resistant. The air temperature and humidity are again important factors for keeping healthy plants. Different plants require different temperature and humidity levels, and different plants require different light levels. There are many excellent resources for general advice for different types of plants. However, there's probably not a database for detailed minute by minute data on how plants do well or not, except for a very limited number of plants. Once we collect data like this, then we will have more opportunity to create such a database. The $30 kit is probably all you need to get started. It has moisture sensors and water pumps, but I decided to add a few more to collect higher fidelity data such as temperature, humidity, and also use a different corrosion resistant sensor. Additional tools that could be helpful for troubleshooting include an oscilloscope, multimeter, and basic tools like screwdrivers and soldering irons. Relatively low cost ones will do for this project, as we are not using the tools to develop the electronics, but just for basic routing. Of course, you will also need a computer, a screen that is separate from the computer with HDMI input and keyboard. A mouse will also be helpful to set up the Raspberry Pi. I did have an interesting incident where I traveled to a different city to work with a friend for a day, and we spent half a day just finding a screen with HDMI input and matching cable. Stuff happens. The lesson is list these things down even if it seems excessively detailed. Often the trick in doing good engineering work is attention to detail. Now, moving on to the software side. These are the software components that we will be using. The Ubuntu operating system for the server, GPIO 0 for the server, Python 3.9 for the server and the client, gRPC as mentioned in the title of this talk, and it's used in the server and the client as well, PySide, which is a Qt or Qt framework for Python. It's also used for the client. I mentioned these in passing here as we will be discussing them in more detail in coming sessions. All of these have alternatives. For example, if we were to develop a web or mobile application client, we could use some frameworks such as Flutter, Angular, or even native frameworks like Swift and Android Java. The important thing to note here is that as designers of a system, we need to understand certain details at a given level of abstraction, while we can take lower level concepts for granted. Over time, as better programming languages and concepts have been developed, we do not need to understand exactly, for example, how memory is being allocated in the operating system. However, at the same time, we now have rapidly progressing mobile device platforms and cloud technologies that we need to understand to be able to build robust distributed systems like this. The more we understand, the better we are able to make intelligent design choices. In many actual engineered systems, a single person may not be able to know every detail, and it is more efficient to work in teams. At the same time, it takes time to understand systems and the environments that they need to operate in, even for teams. So the trade-off is about taking the right amount of time to understand why we take a certain approach. For hobby or do-it-yourself projects, it is fine to follow a tutorial like this, almost as a recipe. We'll now move on to part 3, where we will describe at a high level the system architecture and why we chose some of the options that we did.
So, welcome, Sophie, I think joined recently. So, does anybody have any questions on this part 2? Just taking breaks in between so that it's not monotonous.
So basically, we might need to invest for the hardware, which one is the Raspberry Pi, and the system. Raspberry Pi is like around, you said 140, right? And the system kit, if we buy the system kit, all the sensor will come in the system kit, right? Which will be like $30. So 150, yeah, 150 plus 30. Basically, we around like $180.
Yeah, this is
right?
definitely, this is definitely over-specified, the Raspberry Pi. There are like, I think $30, $40 systems that could work with this.
Okay.
But it will be more time consuming to get it to work because it'll take a longer time to load the operating system and then, to work on it, to download any program and so on. So if you over specify the system, then, it runs faster for your development. But once you have finished development, I think if you wanted to deploy this at scale, where, for example, if I wanted to monitor all the plants in my garden here, there are like literally like 20 or 30 plants in my house, and then there's garden outside and so on. So, if each of these could monitor 4 of them and I need like 20, I would probably try, getting a cheaper one. And then with respect to the other things here, also, these are all hobby grade material. So if you wanted to do this for real, if you were a commercial farmer and you wanted to do this for real, then I think these probes, they're notorious for being difficult to calibrate. So when they say that it's moist, the soil is moist, some days it might be very, very moist. Some days it might be less moist. So to develop a commercial grade sensor that is very accurate for moisture, soil moisture, is difficult. For temperature, humidity, and light, it's a little bit easier because these are more usable. But then you also have to think about how to mount it because the temperature, humidity. I don't know if you know, when you develop weather stations, you have to put it in a certain way in the shadow. Otherwise, you're measuring the sun and not the air temperature. So, you have to develop some standards on how to mount these things near your plants. But to get started as a hobby or to develop the system, I think these are good. If you wanted to develop a real system, I think the computer cost will go down. The sensor cost might actually go up because getting high quality sensors and pumps that can pump water from far away. Maybe instead of a pump, we would use like a valve that you can open, like a tap valve. I forgot what it would be called, but so things like that. The commercial ones might be a little bit more expensive. So each valve might cost $30, and if you have to put N valves for N plant beds, then it might cost more. Yeah, good question, by the way. Anything else? If not, I'll move to the next section.
In part 1, we discussed the requirements for this project and the hardware software components used. In part 3, we will take a high-level view of the system that we will build as part of this workshop. I will also discuss some design choices we made and why we made them. Let me start with a high-level block diagram of the system. In this diagram, I want to emphasize that we are collecting data using multiple Raspberry Pis, possibly connected to the internet using various Wi-Fi access points. Each Raspberry Pi can collect data on more than one plant. Each plant, or a whole bed of plants, can have multiple sensors and actuators deployed. We will call the Raspberry Pis the servers. 0 or more clients can connect to these Pis at any given time. The data is stored locally in each of the Pis. The servers and clients can be geographically distributed with a network delay. The communication or interface between the clients and servers is abstracted using the gRPC protocol. gRPC is a relatively recent remote procedure call system. An alternative to gRPC that is more popular on the internet currently uses REST, which stands for Representational State Transfer. Both REST and gRPC are reasonably similar. I will explain in a little bit why we chose gRPC, but the decision is probably not systemic. That is, we could have chosen either one and the system would have worked. Let us see another alternative architecture. In this architecture, we add a backend in the cloud. Both the data sources, that is sensors, and data consumers, client front ends, connect to this backend. This architecture is prevalent in contemporary designs because of the availability of cloud as a service and many different cloud software offerings that one can use to build distributed systems, almost as if connecting Lego pieces. You must have heard of AWS, Google Cloud, and other popular offerings. For example, many Alexa-connected devices or home doorbell sensors, etc. will not work if the underlying cloud service goes offline. In that way, the cloud services are almost like a utility on top of the internet. I chose not to use this architecture because it is not necessary for this problem. That way, we simplify the system and do not commit ourselves to a recurring cost of this utility. If you think about it a little more, you can see why this architecture is prevalent though. It allows for data to be backed up continuously, and it is possible to scale the system such that the data can be processed and consumed by millions or even billions of users at a time. For example, if we had an application to display the number of COVID patients on a world map, we would expect that millions of people would access the data at any given time. We do not want to burden the data sources themselves to store and serve that data. However, we are talking about a private garden here. Even if all my cousins and best friends want to see what's happening with my garden, I would probably expect only about 10 users to view this data simultaneously. I have to admit, I don't have that many best friends, though I have a lot of friends on Facebook. I'm sure most of them would not find it entertaining to watch whether my orchid is getting the optimum amount of light and water. Okay, let me introduce you to the concept of a morphological matrix. The morph matrix is a tool to express and list the design choices available in a systematic way. At a high level, let's say we were considering these design choices I just discussed. We could consider all 4 options and discuss their merits based on the different relevant figures of merit dimensions like cost, ease of implementation, learning potential, etc. It is typical in an engineering project to have many more design variables. Still, at the same time, it isn't easy even for experienced engineering teams to think about them all at once. Hence, it makes sense to discuss a handful of design variables at a time. Just a reminder, this is the high-level architecture that I chose for this system. Here are some of the considerations that I took into account in choosing this architecture. 1. No cloud computing cost. 2. Faster or more compressed data transfer, which was more important for another project where sensor data was being produced at 50 data points per second from several sensors. For monitoring plants, a slower data rate of perhaps 1 data point per second could be more practical, but we would still want to monitor many plants, and we'd want the data over many days or months or even years, and transfer this data to the client when requested. So there is going to be a lot of data. 3. Interface definition files that produce code. I will talk about this in a subsequent section. 4. There was also a learning component, as gRPC is an up-and-coming technology, and I wanted to get my hands wet on it. We will move to the interface definition and server architecture.
So any questions on this section?
Anyone have any queries? Actually, gRPC, I have never implemented gRPC. The only things I know that Netflix has implemented gRPC, right? So what's the advantage of gRPC over REST?
Yeah, I think many companies are starting to implement gRPC because when you load a website, you may have heard that when you load an app, for example, it'll say loading. It'll take some time. Let's say you start a CNN app, and then it'll take maybe 2 or 3 seconds, or sometimes 10 seconds before all the news loads, and then you can start interacting with it. And before that, you just have to watch some, something spinning or something. So to speed that up, if you don't speed that up, then many users don't stop using it, or they kind of leave for other options. If there's a very fast, responsive website, then it's been shown that that's very good. People are now talking about milliseconds, going from 500 milliseconds to 200 milliseconds or things like that, 50 seconds. To do that, when the web was developed and people started using all this JSON and HTTP, all these are text-based formats. So if you're sending data like 2.5, you're sending the ASCII code for 2, or maybe the Unicode for 2, and then the ASCII code for point, and then the ASCII code for 5, and so it becomes big. And then even though you compress it, sometimes even the compression doesn't work that well because it's like lossless compression, right? So with this gRPC, one of the main things was to have a, go back to basics and say, why do we need that? Why can't we just send binary data, And then if you send binary data, though, now you have to decompress it and deparse it to use in an application. So gRPC kind of provides the framework where it will generate the code to do that compression and decompression. So all the data passing through the network, that's what's causing your application to be slow. Because most of the time the computers are fast. Sometimes the phone or the computer itself is very slow, but many times it's the time required to transfer the data, and this thing is just waiting for all the data to be available. And so gRPC kind of speeds that up. And then another is gRPC uses protobufs that we'll discuss in a bit, which kind of makes it more like a statically typed protocol. In JSON and HTTP, you can agree to something based on a test, like Swagger API test or something like that. But there's nothing holding you to that test, and you can violate the constraints very easily. And many times, many of the things that I have debugged personally is like you were supposed to send an integer in JSON, and it turned out to be like a string, I equals to 3, and instead of I equals to 3, people are sending I equals to the ASCII code for 3, and then it messes up the system, and then it's a long debug process. So gRPC came after, and it aims to maybe make that process a little bit more like a typed language. Some people don't like typed languages, and I can understand where they're coming from. Some people like it, or people may use it at some places, one or the other. But with gRPC, you can say, okay, this part is floating point, this part is, and then it also has the versioning capability built into the system, and you don't have to kind of make up your own versioning type system as with REST. So there's being developed later, lessons learned have been incorporated to an extent.
Yeah, I understood. Actually, I have lots of queries regarding the gRPC, but I don't want to hold everyone because this presentation is a little bit different. So I'm good.
Yeah, thank you. If there are no other questions, I'll go to part 4, looks like.
Hi, welcome back. In part 4 of this series, we will design the interface between the client and the server and discuss the server architecture. The importance of interfaces in engineering cannot be understated. Here is a link to an open courseware with a video lecture by Professor Ollie de Weck of the MIT System Design and Management course. It discusses the importance of interfaces in the design of complex engineered systems. It could be somewhat advanced materials, but it is interesting and I highly recommend it. If you are a beginner though, it is safe to skip at the moment and just follow the tutorial as a recipe. You can start out with changing the parts of the recipe that you understand more. We will use the protobuf, short for protocol buffers language, to design the interface between the client and the server for our system. In this context, this language is sometimes called an interface definition language. The protocol buffers IDL has the concept of a service and request and response messages to the service. The physical server computer or even the same program can have multiple services that it offers. Here is the example from Aveti. In Aveti, the folders are arranged as follows. Aveti is the top level folder. There are separate folders for the client, server, and interface. The interface is defined in the garden.proto file within the interface folder. The generated folder is the folder where the Python code from the interface definition is kept. You can ignore it for now. Now, let's look at the garden.proto file. The first request-response pair is called the heartbeat. The heartbeat request has a timestamp, and the reply also has a timestamp. The heartbeats are used by the clients to check whether a service is reachable or online. Each client will have a list of servers, and it will ask the server, "Are you alive?" using the heartbeat request. If the server is up and running, it will respond with a heartbeat reply. The client will periodically send a heartbeat request, say every 5 seconds, and any server that recognizes this request sends back a response to let the client know that it is there. You can imagine why we call this a heartbeat. Some of the other interfaces deal with, for example, a way to list the plants in a garden, a way to get the real-time sensor readings from a plant, a way to get the historical sensor readings and actuator states in a garden. Getting historical readings could be more involved, and there could be multiple functions related to it. For example, there could be a function to query the date and time ranges of data availability. There could be functions to fetch the average data over a period, a moving average with a given window, or all the data points, etc. There could be a command to water a given plant immediately. In the interest of time, I will not go over the code for these interface definitions. They are pretty similar to the heartbeat interface definition and are available in the GitHub repository. Now, let us go over how the server code is organized. The folder structure of the server consists of some program entry code. Init.py is empty and used to indicate a Python package. Main.py just runs the server defined in app.py. App.py initializes gRPC and starts listening to process requests. It registers Garden as the object that actually services requests. When a request is received, the server code handles the request in the file gardenserver.py. The Garden class in this file has a method for each possible request in the interface definition. For example, here is the code for the heartbeat request. A feature of the code is the use of mock hardware to run and enable testing the code even when actual hardware is not present. For this, we use a design pattern called a factory. We have a configuration file called the serverconfig.ini, which lists configuration parameters such as whether we are running the server as a mock-up system for testing or whether we are running the actual system. List of plants and their profiles. List of automatic control system parameters, such as averaging windows used for the servers. The factory initializes the hardware per the mock parameter. The hardware classes initialize themselves based on the remaining parameters. We will delve into a few more details of how hardware interfaces are handled as part of this series. Thank you.
Yeah, so any questions in this section?
So back to the gRPC. So first we might need to install the gRPC library, right? Definitely.
Yes, yes.
Okay.
The gRPC library, yep.
Yeah. So we need to install that one. And then the configuration that you have mentioned. So the configuration is all the configuration you have mentioned, like moisture, all those things over there, right? So that one I might be like in the next video, might be it will describe how like the system will recognize those configuration, right? Whatever we have defined over here.
Yeah, I don't go into too much detail into that. There is some code in the GitHub, but basically, a Raspberry Pi has a number of these, GPIOs, and GPIO stands for general purpose IO. And then just like USB is a more like a consumer level thing. There are other types of buses. It's called One is called the SPI, Serial Peripheral Interface, and another is called the I2C, something interconnect, I think. I forget what I2C stands for. But so the GPIO is more digital input, and what people call bit banging. You have to, if you wanted to like send some sort of a complex signal, then you have to send it with millisecond accuracy. Then you have to run something that kind of it runs in an operating system that is very time sensitive, so that you have to send in this millisecond, otherwise it won't work. So there will be drivers here that kind of control the GPIO pins. So for each of the sensor categories or actuator categories, we have, right now I'm using the same sensor vendor, so they have the same driver. And so I just need to specify, which sensors are connected to which pins. If we were using like sensors from different vendors, then we would need to specify more things here. And if we were using some sort of extension to the Raspberry Pi, like on top of the Raspberry Pi, if we added an analog to digital converter, then we would need to specify which plant moisture sensor is connected to which input pin of the so that you can identify it. And then in the system, there are multiple Raspberry Pis, and each one has its own configuration file, and when it runs, it loads from that configuration. And right now there's no user interface, so you just edit the text file. That's the user interface to configure this. Because this is like a hobby project, I think that's very feasible for, you don't need like a separate configuration admin UI or something like that. So, it's just configured using text files.
Okay, nice. Thank you, Prakash. I saw Anil has also joined. Welcome, Anil. If no one,
yeah.
Oh yeah, I joined late, so I'm trying to understand this the gRPC. So I was trying to Google it, and it's a good initiation point for me. I couldn't research more before this tutorial, so I could have asked more questions. But yeah, I'm trying to understand.
yeah, even for me, it's new. So I think we are just covering kind of like a basic stuff, because I think most of us are new for gRPC. Even for the Raspberry Pi, I never used the Raspberry Pi itself, right? So all these stuff are new for me. So that's why I'm keep on asking basic kind of like a question to Prakash.
Yeah, I mean, we are more in software, right? So it's hardware, like not much into like. But I see like the GPRC, like gRPC, like we started the server by using Python. So Python is a better way to work with the gRPC.
No, gRPC has N languages. If you go to grpc.io,
I believe
yeah.
Anil might miss our like initial like the one. So gRPC is kind of like a protocol. Like we can compare that one with the REST kind of like a protocol.
Yeah. Okay. Yeah. So it's another type of protocol. Yeah. Nice. Okay.
In part, simultaneous.
Yeah. So it's an alternative to REST, if you will. You can use REST or you can use gRPC. And there's just a little bit of difference.
Yeah, basically I also ask Prakash, gRPC is much more faster than REST, in the sense is when you are sending the data or the receiving the data, gRPC is much way faster than REST.
Yes.
But I think there are both pros and cons. Like I think we need to research on gRPC, but basically that's what the gRPC is.
Okay.
Yeah, I think right now the biggest con that people mention is the lack of tools like, for example, Postman and those kind of things are available for REST. And many people know about these, the 401 means something not available, it's too busy, and then 502 means this, 503 means this, and so on for REST. While for gRPC, people are probably a little bit less familiar about how to indicate like some sort of back pressure in a distributed system, or when something is offline and things like that. So let me move to the next one.
Hey all, welcome to part A of this presentation. I know you must be confused why this is not part 5. Well, I thought I could cover both the interface definition and the server architecture in 5 minutes, but it turns out I need more time. So here we go. We'll go into a little more detail on the code in this segment, into detailed design rather than just architecture. I chose to go into more detail as my project colleagues found it a little more challenging to understand this part of the code. So let me address the problem first. Here's the fundamental problem we're trying to solve. Some tasks could take a longer time to perform than we expect of computer systems these days, where you expect like immediate response. We do not want the server to be non-responsive while the computer performs these tasks. Sometimes this approach is called asynchronous procedure calls. This approach is not necessarily new. For example, here is a code from a book from 1992. The use of the remote procedure call technique as a means for distributing the execution of a program between several machines has become well known and widely used. It provides an easily understood and reliable model for distribution. At the same time, while distributing the code execution, in its synchronous form, it limits the degree of parallelism that can be achieved by an application. An initiating process is not necessarily made to wait while a remote server performs some subsidiary part of the work. Issues involved include the need for the arrangement to be transparent to the user and considerations of reliability and error recovery in the presence of system failures. So you can see some of the concerns there. This is from more than 25 years ago. So these days it's pretty common, but it's still a little bit tricky to program. So here we are not just talking about asynchronous calls remotely. We also want to consider async calls within the server for hardware interfaces and other functions. 3 types of procedures would benefit from asynchronization in our system. 1, hardware access. For example, GPIO operations reading data from our humidity sensor can take a few seconds. 2, storing data. For example, we want to write the most recent data at a regular interval to the files. 3, aggregating time series data. We want to average, find maxima, and so on from the data. In addition, as we are controlling or accessing data from across the globe, asynchronicity is also desirable due to network delays. This is the more remote procedure call part. Rather than using any framework, we use the more basic threading primitives to achieve asynchronicity, and I chose this design due to the simplicity and flexibility. I'd be honored to discuss if you have seen or know of better approaches here. And also, there could be a better name for this method than asynchronous calls that I've used here. As an illustration, let me take the example of reading from the temperature and humidity sensor. By the way, the temperature and humidity sensor I have used is compatible with the Adafruit DHT22 sensor. I relied on an excellent tutorial to use the sensor for a simple program for a hardware test. The tutorial by Emmet in PyMyLife.com is linked in the description. On top of this, we built the threading. In this example, the temperature and humidity sensor is connected to GPIO 4 of the Raspberry Pi. It uses a timing-based digital transfer technique that is handled by the Adafruit DHT library on top of the RPi GPIO library. However, it can take a few seconds to get a single reading that the hardware drivers check for consistently before returning the data. Let us see the code in the rpi_hardware.py file that handles the asynchronous reading of sensor data next. Quickly, the abstract RPi hardware class implements items that are common to the mock as well as actual hardware. Getting the list of plants is needed both for the mock and the real hardware. In this implementation, the mock hardware does not have any code at all because there's nothing extra it does on top of the abstract class at the moment. In the actual hardware, the code creates a thread to read data continuously for each plant. Now let's look at the code in the temperature and relative humidity thread class. It has a single memory location or a bank where it stores the more recent sensor readings and timestamps. And it initializes the hardware interfaces. When the thread runs, the code updates the memory location and sleeps if the allocated time is not over. By allocated time, I mean the sampling time. If a request for real-time temperature and humidity reading comes in, the code only returns the contents of this memory location without actually accessing hardware synchronously. Next, we will see how a similar coding pattern is used to make the client calls asynchronous as well. That's in part 5. Thank you.
So before I move to part 5, any questions on the last part? Oh, there was a lot of, yeah.
So before you have mentioned the cloud, no, I was thinking when you are saying the memory and everything, if we want to I mean, right now this project is kind of like small, so we do not need to worry. But if the project is big, if we have lots of data, definitely we need to save somewhere, like the past somewhere, right? That might be in that condition, the cloud might becomes in picture where we could send the data and everything, right?
Yeah, the data, the scale of data currently is
as a high school.
let me see if I can bring up that diagram.
The screen that is separate from the computer with HDMI input and keyboard.
Maybe somewhere here. Yeah. So for each plant, if we are generating data every second and each data is like 100 bytes, then 100 bytes times if we are doing for a year, 100 times 60 is minutes, and then 60 is hours, days, 365. So that many bytes. So 1024 is kilobytes. And megabytes. So it's about 3 gigabytes of data per year. And the Raspberry Pi that we spec'd has 128 gigabytes of memory, but obviously also you don't want to lose it if it's like if the hardware goes bad, so you want to back up. But you can also use you could store the data or create another process to copy over to like a Google Drive like thing and use a free Google Drive to kind of just for backup purposes, and you don't access the Google Drive directly. And also I've written other programs where from the Python code you access the Google Drive directly, so you could store in Google Drive and then you get a few gigabytes, like 5 or 10 gigabytes for free that way. But if you're doing it on a larger scale, then there's no alternative to paying for it. And then people have said that it's not that expensive, like with the S3 buckets being really cheap, that if you use just for storage, then it's not that expensive. But if you start using it for like a server machine or a backend for a cloud with queues and with servicing a lot of requests from a lot of users, then it quickly starts becoming very expensive. But if you want to use it just for storage, then I think it's practical to do at $5 or $10 or $20 a month.
The question, like, so it's not only storage, right? You want to access the data too, right?
Yeah. So I think just before
now,
you joined, I discussed that currently this is in this system. I expect that only 10 people will use the system at a time, because it's my private garden, and then who would be interested to know whether my orchid or my spider plant or my cilantro got enough water, and the lights were enough or not, and so on. So only I would be interested, basically, maybe my wife and me. So so it's more like a personal system than for something in the public. But if we wanted to do this where this is like a for example, a botanical garden in New York, and we want to put it online where all the people who visit the botanical garden want to know whether this special plant got enough water or not, then you will need this kind of architecture. Yes.
Yeah, I mean, nowadays, like, everyone wants to, like, know, like, even we go out of house, like, we want to know whether our garage door is open or no. All the sensors, there are so many sensors, and we try to access from a mobile app, right? So
yeah, okay. So in this architecture also, you can access from a mobile app. You just need to use the right library to use, to connect to the backend. You can connect directly. You don't have to have a cloud in between. I think a lot of the companies that provide this have a cloud because they want to, like, provide a more robust service and want to charge for the service.
Right.
Yeah, so their business model is that you charge for the backup and you charge for the web-based access, and you can't usually access the data without their protocols. So if you let the data stay at whoever is the customer, then your business model doesn't work, because then people can switch or buy their own hardware and stuff, right? So I think also due to their business model, they want to store the data in the cloud. That way it's like the data, they have the data. And that's one of the, because my doorbell, like, these days there are applications where the police force is using the Ring data from everyone, right, and so on, and such. But with this architecture, it's kind of like a private network, just the Raspberry Pi and your client, and there's no cloud in between. If you want, you can replicate the Raspberry Pi for data backup.
Yeah, I mean, yeah, right now it's a private. I mean, once we have data, I mean, we can always make it extend, like, we can add Google Cloud later, or we have like some free database like Firebase Google provides. Yeah, I mean, you're right. I mean, once we have the system architecture, I mean, accessing the data is not a big deal. I mean, we can always extend that later.
Yeah. Yeah.
Okay, guys, let's do one thing. Let's extend the time because it's been 10 o'clock, but let's do another. Let's extend until 10:20. I think we have like the, if everyone
I have only one more remaining.
Oh, you have only one more? Okay. Oh,
Yeah,
okay.
I planned for 8, but actually I only got to make 7. Or
Okay.
yeah, I have only one more remaining, and the rest of it I'm gonna say, hey, subscribe to my channel, and
Okay.
I'll put more in there.
Okay.
Yeah.
Okay.
Welcome back to part 5
yeah.
of this
Yeah. So this is the final one I managed to produce for today.
Tech Talk. In this section, we will look at the code arrangement and architecture of the client. I call the graphical user interface, or GUI, the client in this talk and the code. There is a common problem that we want to solve when designing software for a GUI project. Problem is having a responsive system. Otherwise, it would just be a command line interface where you enter a command and wait until it ends before you can do anything else. It is especially true for clients that access data or need to command remote or cloud systems. If you are writing a calculator program that did things that only take milliseconds, then this would be less of a problem. For Aveti, the code for the client is currently just in one file called mainwindow.py. I wrote the client using PySide 6, and I also used the Qt material library to mimic the material design system. The code to enable this is not that complex. I will skip the layout management and basics of building graphical user interfaces using Qt, as there are many excellent tutorials on this topic. I found this one by Real Python that is a good beginner tutorial on the subject. I will focus on some topics that are often not covered in many tutorials because I used my own flavor of the method of solving the particular problem. This is not too unusual though, as more often than not, there are infinite ways to program a solution, but many of them are somewhat related. Again, I would be honored to discuss better or much better ways to do this. I have a hunch that I haven't yet used the best method, as I don't work in Python Qt GUIs daily. Now, on the way that I use to solve a problem, first, I create a base class called base gRPC thread. It has a signal called done, which we emit when we have either received the response from the server or there is some network error or some other error. Backtracking a little bit, Qt has a beautiful way to address event-driven programming through the system they call signals and slots. Again, there are other excellent tutorials on this matter. I found a fun one by Velcode that I will also link to the description. Quick one-sentence refresher. 0 or more slots can connect to a given signal. When a signal is emitted, the methods in the slots are called one by one. Now to the thread run method. The code is boilerplate for calling gRPC using the generated class files. Another quick mention, since I have not mentioned this before, the make file has the command to generate the gRPC code using Python gRPC tools. So I only have to type make gRPC then if the interface definition or protocol between the client and server is changed. This code was inspired by Martin Heinz's implementing gRPC server using Python that I will link to the description of this video. Now back to my code. I create a bunch of thread classes from the base classes, one each for each request that I need to make to the server. For example, here are the ones for the heartbeat, water plant, and get data. If I need to pass an extra parameter, like this plant ID, I pass it to the constructor and store it until I need to make the remote procedure call. Now, when I'm initializing the GUI, I create a timer called the heartbeat timer. When this timer beats, I spawn a new thread to asynchronously get the data. The done signal is connected to another GUI method to update the graph, for example. Here is a video of the running system. You can see that the sensor data are not evenly spaced, as we record and pass the last time we were successful in reading the sensor. If the network is down for a while, or if it takes time to connect to other servers while data from a given server is available, this approach handles the responsiveness of the GUI gracefully. Even though it takes a few seconds to get the data, because we have several levels of asynchronous calls, the GUI is still responsive as one expects in a modern bug-free system. Now we move to the following sections: integration and testing.
Yeah, so the integration and testing, I plan to actually implement this and maybe even create a 3D printed vase for the plant so that the water tube is not visible and the sensor is embedded within the pot and so on. So, when that happens, I'm going to update the channel and put a few more videos of, right now it's working kind of in a rudimentary manner, but, I'm considering it my summer's project over the next 3 or 4 months to do this a little bit more properly and also discover, as I said before, the sensor hardware, how durable they are and how accurate they are, because, I've heard that they're not very durable. And to get more better sensors, especially the moisture sensor could be interesting. And then I'm actually working on another project where we have near infrared sensors for monitoring biomass in plants and so fruits and so on. So there are different types of sensors that are much more expensive that I could integrate into it. But for now, this is it. And thanks, everyone. If you have any final questions. In fact, I remember one other use of gRPC type things. For example, with Bluetooth, if you have a battery operated device, then Wi-Fi actually takes thousands or hundreds to tens of thousands of times more power than Bluetooth. So if you made a Wi-Fi headphone, then the battery would only last a few minutes instead of a day or so. So because Wi-Fi requires much more power. Now, if you have Bluetooth, then the data rate is much lower. And if you wanted to send the data, for example, voice for Alexa-like things and so on, then if you didn't use something like gRPC that has compression, then if you started using REST in Unicode characters and so on, then it will become it will take much more power, and your battery life will get reduced. So a lot of these peripheral devices like headphones and sensors that you wear on your body use gRPC-like thing. Maybe because it's proprietary, each company has their own thing. But then more recently, I think I've seen people start use more open standards. So any other questions?
Yeah, so if not, then what I'll do is first, so on the behalf of the member of our group, I want to thank Prakash for this insightful presentation. Really, you provide so many information and all those things. Thank you for that one. Let me give short introduction about our next presentation. Our next presentation will be on July 24th, Saturday at 9 p.m. EST. The presenter, Anusha Sridhar, will give the presentation on enhanced biometric for ATEM. Anusha looks like already left today's session, but she has provided me the short description of her presentation topic. Let me read on behalf of Anusha. Let me check. Okay, here it is. So enhanced biometric for ATM is a method where we use our fingerprint for accessing the ATM machine in place of our PIN code. Provides more secure way to access the ATM. This method uses an algorithm called minutia, which will detect the detailed fingerprint and compare it with the database with the bank for verification. If detected, you will get access, if not denied. Work is in progress for this project. So she is going to provide a presentation on this topic on July 24th, Saturday, 9 p.m. EST. So do you guys have any queries to Prakash or to me or anything else?
No, I'll just say like thank you for organizing this one, and it's very helpful. And some of the details are really like high level, like I mean very in depth, but it's a good way to like know the new technologies and to know how it works. Thank you, Prakash, and thank you, Soren. Yeah,
thank you very much, Anil. You are always welcome. And one more thing is like I have also mentioned at the beginning of the presentation, I have also created the Slack and LinkedIn group. And over there, if you have any kind of queries regarding the presentation, or if you have any kind of like a comment or any kind of like queries regarding this presentation or regarding any kind of queries to Prakash, you can shoot in the LinkedIn or in the Slack. I'll provide you that link to not only you, everyone like who participate on today's presentation. I'll send the email to everyone. Anyone have any further queries? If not, thank you very much for participating in this presentation. Thank you very much. Have a good night. Bye.
Thank you. Thank you, everyone. Bye-bye.